Mr. B. Dhanasekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. In this episode, we are going to have the theory of computation subject. It's a very important subject in which we are studying about the various theories behind the computation. We should know what is a computation and what is the meaning of the decidability and what is the meaning of that is checking whether a string is there in a language or not, like the membership and so many things. As far as these kind of problems are concerned, it is not just doing computation, but it is also deciding whether a string is there in the language or not, or it is just something like decidable problems, whether the solution for a problem is yes or no. In all these cases, we need some kind of recognizers or machines which are actually doing the job. Suppose if I am doing some computation, I need some kind of machine for doing the computation. Or if I am testing whether a string is there in a language or not, I need some kind of recognizers. Or if I have to find out the answer for a question whether it is yes or no, I need once again some recognizers. So what these recognizers we are having and how they are all solving these problems. These are all the things we are having as far as this subject is concerned. Another thing is regarding the computability. Suppose if I am giving a problem, we have to find out whether the problem can be computable or not. We cannot say that all the problems available in the area are computable. If there is a solution available for the problem, then we can say that the problem is computable. If we can't find out a solution for the problem in a stipulated time, then the problem is coming under non-computable category. But it is possible to find out whether a problem is computable or not by using this subject. Another thing is decidability. Suppose if you are given a problem, to get the answer, whether how long it will take, or will you be able to get the answer in after some amount of time or not. After getting the answer, will the problem or will the device will come to halt or not. So many things we have to find out. For all these kind of problems or the questions, we will be having answer from this subject. Let me start with what the outline we are having as far as the subject is concerned. So the first part of the subject is the formal languages. Because as far as any problem is concerned, we will be having a question like whether a string is there in a language or not. So language is having a most general definition, the set of all strings or the set of all sentences or the set of all statements. We are giving a string and check whether it is there in the language or not. So first of all, we should know what kind of language we are talking about. The language which we are talking about is not the conventional languages like English or Tamil. Here we are talking about the formal languages. A language is said to be formal based on the alphabet from where the language is defined. So only when, that is after talking about the formal languages, we can think about the corresponding recognizers for that. As far as formal languages are concerned, the basic class of language from that set is going to be the regular language. So in the case of regular languages, we want to have a recognizer for that. The name of the recognizer for the regular language is the finite automata. It can be otherwise called a device which is normally used for recognizing the regular language. You can call languages regular if there exists a finite automata, or given a finite automata, the language recognized by the finite automata is called the regular language. So that is going to be the very first class of language and the very first class of devices which we are going to talk as far as this subject is concerned. The next one is the context-free grammar, or the device equivalent for the context-free grammar is going to be the push-down automata. As far as push-down automata are concerned, it is going to recognize another class of language that is next to the regular language called the context-free languages. So to recognize the context-free languages, either we want to have the context-free grammar or the push-down automata. The difference in between the finite automata and the push-down automata are lying on the existence of a stack. So just because of we are having a stack along with the automata, the capability in terms of the language recognition power is getting increased. So we will be able to recognize regular language plus some more languages. So the entire set of language recognized by a push-in automata is called the context-free language. So beyond that, we will be having another type of language called the context-sensitive languages, and there will be a class of devices called linear bounded automata, which are used for recognizing the context-sensitive languages. And over that, we are having languages called recursive languages, recursively enumerable languages, and those type of languages are recognized by a type device called Turing machines. So that is another part of our subject. So Turing machine is almost very similar to a computer. So whatever a computer can do is possible with the help of a Turing machine. It is a simple theoretical model of a computer. So we call it as Turing machine. It is named after the person who has proposed this Turing machines. And the very last part of the syllabus or the subject, that is content, is going to be the hierarchy proposed by the Chomsky. So I talked about the formal languages, and there is a hierarchy of languages coming under the formal languages, starting from regular and is going up to recursively enumerable languages. This hierarchy is proposed by Chomsky. That's what we are calling about, and that is hierarchy is Chomsky's hierarchy. And this is what the entire content of the theory of computation syllabus, which is prescribed by the UGC. So next topic is going to be the objectives. What are the various objectives of this subject? Already I talked about we are studying the various machines or the recognizers and various class of languages. So for every class of language there will be corresponding device available, and we want to know what can be computed and what cannot be computed, or given a device what is its capability and what is its incapability. If I am giving you the finite automata, it is capable of recognizing regular languages, but it cannot recognize the language which is not coming under the regular. Suppose if you are giving a context-free language for which we cannot construct a finite automata, then there is no point in going for constructing a finite automata for recognizing that language. So we want to find out what is the capability and what is going to be the limitation of the devices. So that is the first one. And another thing is we are talking about the abstract models. The device which we are talking about, like whether it is going to be the finite automata or it is going to be the push-in automata, they are theoretical in nature. But when you want to go for implementation of all these things, we need to write only programs. So the devices, finite automata or the push-in automata or the Turing machine, they are theoretical in nature, and we have to study all these theoretical models. That is the second objective of this subject. And another thing is how we are applying all these that is your models. Models may mean the abstract models into practice. So if you are given a regular language, we should be able to construct its corresponding device. How do we construct? We should know that finite automata is solution, and once the finite automata is available, we can say that we have the model in theory, but we want to make it as practice, or we want to make it that is possible for implementation. We can transform it into a program, and the program will do everything. All these things are going to be addressed as far as the subject is concerned. So before getting inside the subject, let me introduce some of the personalities whose contributions are playing a major part in this subject. The first person who I am going to introduce is the Noam Chomsky. Actually, he is very well known for the generative grammar, universal grammar, and Chomsky hierarchy, as well as the context-free grammar. Even the context-free grammar is proposed by the Chomsky as that is, we are having a class of language called type 0, then type 1, then type 2, and then type 3 languages. The type 2 language is the one which is proposed by the Chomsky. Initially he called it as type 2 language, but later it was named as context-free language. So he is a well-known person for the Chomsky's hierarchy, over which we are having the complete that is formal language classes. We are starting from the regular and we are going up to the non-recursively enumerable languages. The entire class hierarchy of languages were proposed by Chomsky. So in that aspect, he is well known as far as our subject is concerned. The other guy whom I am going to introduce is the Kleene. So over the entire subject we will be talking about Kleine's closure, we will be calling it as closure. Actually if you are that is taking a string, then how we will be forming more and more classes of strings or more and more bigger languages from the given string. Maybe from a simple letter, or it is going to be a string, or from an alphabet, how we are forming the strings. So it is only with the help of the Kleine's contribution. So he is actually known for the recursion theory, and he is the inventor of the regular expressions, and he is known for the Kleene hierarchy, Kleene's algebra, and the Kleene star. So all these topics we are having as far as our subject is concerned. The next person whom I am going to introduce is Alan Turing. He is a very important person as far as our subject is concerned, because wherever you are talking about the computability, that is whether a problem is going to be a decidable one or it is not going to be a decidable problem, we need the help of the Turing machines. The Turing machines were proposed only by Alan Turing, so, and he is very well known for cryptanalysis of the Enigma, which is very famous as far as during the World War II. He is a well known person as far as the theory Turing is concerned, Turing what is concerned, and Turing for Turing test also he is very well known. And another area where he has studied very well is going to be the halting problem. So given a problem, and whether the problem, that is the device for the problem, is going to halt or not. So we can say that a problem is going to halt if the answer is available, and what will happen suppose if the answer is not available, will you be able to halt or not? So if it is guaranteed to halt even in the presence of answer or in the absence of answer, then it is going to be a problem called a decidable problem. And if not, that is for the answer, if it is available, it is going to halt. If the answer is not there, if it is not going to halt, then the problem is coming under the undecidable category. So those things are actually proposed by Alan Turing. And the last person who I am going to introduce is Cook. Actually he is very well known for the NP completeness, and actually it is the, we are classifying that as where a problem is coming under the polynomial category or it is going to be an NP category. And another question is about whether a problem, that is NP problem, will become a polynomial problem or not. So that is still, it is going to be an open question, and if you find that one NP problem is becoming a polynomial problem, and then every class of that is NP problem can be proved as a polynomial problem. So it is not possible to show that the NP problems as polynomial problems. Those things were actually proposed by Stephen Arthur Cook. So these persons are very important as far as our the subject are concerned. And now I am into the subject. So let me start with the definition for the formal languages. So what is the meaning of a formal language? If you want to say formal, the first thing is we have to define what is the alphabet for the language. So for any language, basically if you are talking about English, there are 26 number of letters available. So if I am writing some symbol which is not there in the, there is 26 collection, then we have to interpret that in the way that is which is needed for the language. Maybe I am saying that dot is another symbol which is introduced in the language. We will be calling it that is dot, and it is used for denoting the end of a sentence. So I have to give the own interpretation for the particular that is symbol. So if a symbol is just like that introduced and there is no meaning assigned for that, then the language is not going to be a formal one. So if I want to call a language as formal, then definitely the alphabet must be predefined. The definition of alphabet, it is actually following the coming slides. It is going to be the set of all symbols. So if the string, that is language is English, then at least we want to have 26 number of, that is letters from the English alphabet. So here if you are talking about the binary language, suppose if you are talking about the, that is executable files, then we need to have an alphabet with 0 and 1 as the symbols. So any string you form out of the, that is alphabet 0, 1, it is going to be the language called binary language. It may have, that is one symbol, or it may even have 0 number of symbols, or it may have any number of symbols, and the symbols, when they are combined in the order to get strings, and those strings are actually called the language. So the general definition for any language is going to be the set of all strings. How the strings are all made? The strings are all made from those symbols in the alphabet. So what the alphabet we need, it is fully depending upon the language. If I am defining that I am going for the language called the binary language, then we can go for the, there is symbol, there is definition of the alphabet, there is 0, 1. So here is a definition for the formal language. It is going to be a language over an alphabet sigma, and it is actually made up of sigma star. Sigma star means entire collection of strings. Actually the set of all words over the alphabet. And what is that alphabet? Alphabet is the one, actually it is called the finite set of symbols, or you can call even them as letters, but it is very important that they must be finite and there should be symbols. It cannot be empty. If it is empty, you cannot make any, there is string out of it. So that is the definition for the rest language. Let us go for a short break and we will continue lecture after the break. Welcome back. what we have seen earlier is the definition for the language. It's going to be the set of all strings from the alphabet. Let's see that is what is going to be the examples, few examples for the language, that is formal languages. So any collection of strings can be language, but if you want to call it as formal language, then we need to talk about what is going to be the alphabet. I talked about the binary language or the executable versions of any that is computer that is generated files. They are having only the simple zeros and ones. So any set of all strings from the alphabet 0, 1 is going to be that is a formal language. You can think about the set of all there is operators. If I am talking about the operators available in C language or in any computer based language, it's going to have only finite number of symbols, and those symbols are having their own meanings. So that is going to be a that is formal language. You think about a program which is written in there is computer language, that is C. So you cannot just like that mix up so many things in a program, and if you are doing so, we cannot claim it as a program. We want to make it as a program, the program must be translatable by any predefined compiler, and for that we want to know what are all the basic symbols available in the that is supported by the language, what are all the statements supported, the operators supported, the constants, identifiers, those things. It's all predefined. We have syntaxes and we have rules for forming identifiers, we have rules for generating that is constants. So based on that only we are generating the various tokens available in the language. Because we are already having the basic sets of symbols, operators, keywords, tokens, everything, we can claim that language as a formal language. So these are all the examples, set of all strings from the binary alphabet 0, 1, set of all operators, the entire set of keywords, it's also going to be finite, and the set of all legal programs in C. Actually it is going to be an infinite set. So the formal language not necessarily be always finite, it can even be infinite also. And now we have to find out what is the definition for theory of computation. When I start the lecture, I told you that is the computation. What is the theory behind computation? That is what about the objective of this subject. And here we have the definition. We have to find out that is what are the capabilities and what are all the limitations of computers. Not necessarily be it's computers, it can be any there is a device. And the device it's normally is going to be the abstract one, and we can transform it into the practical scenarios. So just like the Turing machine, it's going to, when it is converted into a theoretical, the practical one, it's becoming a computer. So what it can do and what it cannot do. And next one is, we have to find out how efficiently it is carried out. That is also very important. Most of the time we will be concerned with there is the languages and strings. We have to find out whether a string X is there in the language or not. Okay, suppose if I am saying that the set of all even numbers. The set of all even numbers, when they are represented in binary, there will be a binary pattern available. Most of them, the binary patterns are ending with a 0. If it is ending with a 1, then it is going to be a binary equivalent for odd number. So we have to find out whether the given number is going to be a even number or not. So can we check out that is the entire infinite set, that is as far as the even numbers is concerned, it's going to be infinite. Can you check the entire set of infinite numbers? It's not possible. So now we have to find out the pattern, how an even number looks like. Whether the set of all there is the set what we are having in the even numbers is going to have a match with this number which is given for it. If I am giving that is 1 0, there will be match with some of the strings available in the given set. So if there is a match, then we will immediately say that it is going to be there is even number. If it is 1 1 you are given, then we will not be able to find out there is a match for this pattern with the pattern existing in the given set. So we have to find out whether the string is matching with the set of all strings available or not. If there is a match, then we will say that the problem is giving you the answer yes. If not, we will get the answer that is no. Not only finding the answer, we have to find out how efficiently we are that is solving that. If I am going for a finite automata, I can construct a finite automata with 10 states, or I can go for even 20 number of states. If I am finding that it is possible to construct a finite automata with 10 states, why should I go for 20? So that is what the meaning of that is efficiency. How efficiently we are finding or we are deciding whether a string belongs to a language or not. So for that also we are having the answer from the subject code is going to be that is theory of computation. Now we should know that is what is the meaning of automata theory. So what we are talking about automata and what we are talking about the automata theory. Actually it is completely studying the abstract machines, and the abstract machines means it's going to be a theory of a practical thing. It can be a theory of computer, or it can be a software, or it can be even a hardware. So that is what your abstract machine, and studying these abstract machines is going to be the theory of automata. and we have to find out what is the meaning of a problem as far as our subject is concerned. So wherever I am talking about a problem as far as this subject is concerned, it is deciding whether a string belongs to a language or not. It can be a regular language, or it can be a context-free language, or it can be a context-sensitive language, or it can be something recognizable by a Turing, a recursive language or a recursively enumerable language. So you have to find out whether the string belongs to the language or not. That is what going to be the problem. What language it is and what string we are checking, it's all depending upon the problem instance. And the next is the various elements of automata theory. We start with what is a symbol, and then we are having strings, so many things. A symbol is going to be an abstract entity. Actually, it is not having any specific meaning. It's all completely depending upon the context. For example, we can say that there is a circle available. A circle in the English alphabet is having a meaning that is O, and if it is going to be a mathematical object, it is going to be called a circle, and in different scenarios it will be having different meanings. Maybe sometime we will call it as a dot. A small circle may be treated as a dot. So it's the interpretation given is fully depending upon the context. A symbol by itself, there is no meaning, but the meanings are assigned by the contexts. So that is what called a symbol. So we cannot further that is define that as far as the symbol is concerned. You can think about the examples like 1, 2, 3, A, B, C, D, plus, minus, so many things. Actually, they are all the examples for symbols. And the next definition is actually for the alphabet. It's going to be the finite non-empty set of symbols. Generally, we give the notation that is sigma for that is representing the alphabet. So if it is binary alphabet, we will be having 0, 1. And if it is something like English alphabet, we will be having the set of symbols like A to Z. If it is going to be digits, then we will be having the symbols from 0 to 9, etc., etc. So based on this alphabet only, we will be defining the languages. What a string is? A string is going to be a finite sequence of symbols. We should never define a string as finite collection of symbols or finite set of symbols. A string means definitely it should be a finite sequence of symbols. Suppose A, B, C is a string, and B, C is going, A is going to be a different string, but the symbols involved in both the strings are going to be same. So we should always define the finite sequence of that is symbols, that is a string is concerned. It can even be empty also. Suppose if it is empty, then we will be having a string called the empty string, by which there is no position for storing any symbol. We call it as empty string. That can also be a string. As far as the empty string is concerned, the alphabet doesn't matter. Whether the alphabet is going to be English alphabet, or it is going to be digit, or it is going to be operators, empty string is not having any relation as far as the alphabet is concerned. The next, it is going to be what is meaning of length of a string. It's also a very important definition as far as this subject is concerned. So generally we will be saying that it is going to be the number of symbols, but number of symbols is not going to be the exact definition for that is length of the string. We should say that it is going to be the number of positions available for a string. Maybe for example, if you are having that is ABA, the number of symbols available in ABA are only 2. That is A is a symbol and B is another symbol. But the number of positions available for ABA is going to be 3. You can store 3 symbols. What those symbols are, it's not going to be matter. As far as ABA and ABC are concerned, though they are 2 different strings, the length of the string is going to be same. So the definition of defining like number, that is number of symbols, it is we cannot make difference as far as these kind of things are concerned. So we should be very clear in defining the length of the string. It's going to be the number of positions available for a string, that is for symbols in a string. So that is the definition of the length of the string. Here the example, that is we are having 0, 1, 1, the length is going to be 3. As far as this epsilon is concerned, it is a notation used for describing empty string. Epsilon by default is not a symbol. It is a notation used for defining empty string. So there is no position for storing any symbol as far as empty string is concerned. So the length of the string is going to be 0 here. And the next is for powers of an alphabet. That is how, that is from a simple alphabet, how we are building that is more complicated languages. Maybe by using that is the symbols once or twice or thrice for any number of times. So we used to denote the notation that is sigma power I, that is going to be the ith power of an alphabet. If it is going to be 0, 1, then we will be having sigma power 0, that is epsilon, it is independent of the alphabet. If it is 1 means they will be having that is 0, 1, and if it is 2 we will be having 4 number of symbols, that is strings. And sigma star is actually the combination of or the union of 0, sigma power 0, 1, 2, keep on going, and we call it as clean closure, and this is sigma power plus is going to be the positive closure. The difference in between the sigma power star and sigma power plus is lying on whether we are including this sigma power 0 or not. If 0 is included, then it is star. If 0 is not included, then it is going to be plus. We can make use of this plus from the star just by introducing, that is one more, that is sigma. So if it is sigma union sigma power 1 to sigma power etc., then we will be calling it as sigma power star. So the next is the language definition. It is going to be the set of all strings chosen from some alphabet, that is going to be sigma, and sigma star is the set of all strings. So if we are having a special notation, that is pi, which is normally used for denoting the empty language, and empty language means we do not have anything at all. Empty string means there is no position for storing a symbol, but when you are going for empty language, there is no question of having even a single string at all. So how we will be representing that? We will be having a notation called pi that is used for denoting the symbol, that is our empty language called empty language. So empty language is once again completely independent of the alphabet. Whether the alphabet is going to be binary alphabet or it is going to be something like that is A to Z or 0 to 1, whatever it is, then we need not bother about what the language, that is alphabet is. The language is not going to have anything. The notation used for denoting empty language is called the pi. So now it is, we have the examples for few strings, that is first one is going to be epsilon. It is a language consisting of only empty string, and the next one is the set of all binary numbers whose value is going to be prime. So 2 is a prime, 3 is prime, 5 is prime, 111 is prime, and 1011 is also prime. So we can form any collection of strings from the, that is alphabet. So if it is going to be binary alphabet, this kind of strings can be generated. If it is A to Z, we can form the strings like that is you can think about the keywords available in a language like C or C++. We can form various keywords from the English alphabet. If it is any number like integer or a floating point number, or it is going to be that is decimal numbers, whatever it is, we can form with the help of the alphabet called, that is 0 to 9, with the help of some dot or some symbol for exponentiation. In addition with that, we can have even the signs also, plus or minus. So by including those set of symbols in this language, we will be able to form any collection of strings. So let me go for the conclusion of this particular episode. We started with what is the definition of the theory of computation, and what is the formal language, and what is the meaning of an alphabet, and how we are making use of the formal alphabet for forming strings. The strings are made up of the alphabets. Alphabet is going to be a finite set of non-empty symbols, and we have seen the definition of symbol also. The symbol by default, that is, it's going to be some abstract entity for which the meanings are completely defined over the context. And after that, we have seen the definition for the language. Then the languages like empty language we have seen, and empty string we have seen. Then empty, that is how we are forming the finding the length of the strings. So those things we have seen. As far as the question component of this episode is concerned, we may have something like the definition of language. It may be possible, or you can think about what's the meaning of the hierarchy of formal languages, or the definition of the formal language. The hierarchy of formal language, actually it is starting with the regular language and it's going up to the recursively enumerable cases. There is regular language, then context free, then context sensitive, then recursive, then finally it is going to be recursively enumerable. So even if you find that language is not recursively enumerable language, we have to go for calling it as non-recursively enumerable language, for which actually we do not find out any device at all. Then we should know about the various language recognizers like the finite automata, or it can be even a Push-in automata, or it can be the Turing machine also. So Turing machine is not only used as a recognizer, but it is also used as a computing device also. So that is what the end of this episode. We will see the remaining topics in the coming lectures. Thank you all.